starting chapter 8. So chapter 8 first is going to look at exponential models, which is today and tomorrow. When we come back from break, we're going to look at those logarithmic functions. So I know a lot of you on your CDT saw LOG in some of your questions. The logarithm is actually the inverse of an exponential, just like x squared and square root of x are inverse functions. The exponential, which we're looking at today, and the logarithmic, which we'll look at when we come back, are inverse functions. So exponential models, the standard form for one is y equals a times b to the x power. So this is going to be our main focus of a general form equation for the next couple of days. We've actually never looked at these before because we've seen like x to the second power, but we've never seen like 2 to the x power, where the exponent is a variable. So that's what the definition is. It's just something that's in that format. Okay. Now there's two types. There's exponential growth, and that's where the function grows exponentially. It gets much larger very fast. Now this is from the graphing calculator. It actually should be extended and have an arrow going to the left. Now notice the graph never goes underneath the x-axis. So it never gets smaller than 0 on the y. And we'll see why whenever we start looking at these tables. So the exponential growth is when this b variable is actually greater than 1. So it could be 1.1, could be 5, could be 20. Now exponential decay is when you're starting with a large number and it's decreasing at an exponential rate. The same thing happens. It actually never gets below 0. It's just going to get very, 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 very small. This occurs when b is less than 1. Today we're just going to focus on the exponential growth. We're going to graph them by hand. Obviously our graphing calculator could just do it for us, but we want to practice by hand. We're also going to practice writing equations from word problems in this form. And we'll also write equations from this using 2 points. So example 1 wants us to graph the exponential equation y equals 2 to the x power. Again, if you were using your graphing calculator, you would type this in your y1. You could press second graph or second table, and you could just copy down the values and plot them. But I want us to practice them by hand because some of you had trouble on the no graphing calculator part because you're just relying too heavily on your table. All you're going to do is plug in values. These are usually the values that I pick to plug in because they give me an idea what's going on, you know, in the negatives at 0 and in the positives. So we'll plug these in by hand. So 2 to the x power would be 2 to the negative third power. What happens with a negative exponent? It becomes a fraction. Very good. So this will move to the denominator and become 1 over 2 to the positive third power. Then we would evaluate 2 to the third power, which is 8. So this would be the ordered pair, negative 3, comma 1/8. Do the same thing for all the other values. 2 to the negative 2 would become 1 over 2 to the positive 2. Then we evaluate to get 1/4. 2 to the negative 1 become 1 over 2 to the positive 1, which is just 1/2. What would 2 to the 0 be? Anything to the 0 power is? No. 1. Say x to the 0. Any value to the 0 power is always 1. That was one of our exponent rules. So that'd be 0, 1. And then obviously the other ones, 2 to the first is just 2. 2 to the second is just 4. And 2 to the third is 8. And then we just go and plot those points. Now, sometimes you will have to scale the axis. This one we don't have to because the numbers only go up to 8. But you'll see below, sometimes they go up to like 1,000, 2,000. So you may need to, on your homework, count by like hundreds or fives, and you'll have to pick that after you do your table. Now, also when we plot this, obviously plotting 1/8 on the graph is going to be very much an estimate. So is the 1/4. So 1/2. Then we are going to do our very best to complete a curve for that. It should have arrows on both ends. Okay, so again, just make sure that when you draw this, you never show it going underneath the x-axis, because it cannot be negative. The reason it can't be negative is no matter what number you plug in for x, let's say we plugged in negative 200, you'd end up getting 1 over 2 to the 200, which is still a positive number. It's just very small. Okay. Now let me show you in the graphing calculator too. We're going to need those later, but so we have 2 to the x typed in our y equals. Now if you go to your table, let me change my table set. Oops. All right, so you can see that the values match up with what we saw in our table. Now watch what happens whenever you go further past negative 3. The number keeps getting smaller and smaller until it actually goes into scientific notation, because it's like 0.00000, really, really, really small. It never gets negative though, okay? So that's why when we look at our graph, and if you were to graph this on your calculator, it looks like it stops. And that's because it's so close to 0 that we can't see it in our graph, but it is still there. So what this is actually called right here, and we'll talk about this a little bit more tomorrow, this right here is called a horizontal asymptote. And it's basically an imaginary line, obviously horizontal, that this curve will get so close to touching, but it never touches because it just keeps getting smaller and smaller and smaller. And you keep making the number infinitely smaller so that it never actually becomes 0. Okay. The next one is basically the same thing. The only thing you have to be careful with this is that you do use your order of operations. And remember that exponents come before multiplication. So for this one, we would plug in, I already have these done just for the sake of time. We'd have 4 times 2 to the negative third. Make sure the only thing that you're moving to the denominator is 2 to the third. So it would become 4 over 2 to the third. And then you would evaluate 2 to the third, which would be 4 over 8, which then becomes 1/2. So see if you guys can complete that. And then graph it. You will need to scale your axis once you're done, because you'll see what your highest y value is, and you'll need to be able to fit that on your graph. And on your homework, you don't have to write every number. As long as I see what you're scaling by, you could just get up to the number you need to get to. I know it's time consuming and it's hard to fit sometimes, which you'll see on some of the homeworks that I put it on the side just so I don't mess, I can still graph my points. Now remember, when you do this, when you graph 1/2 and you're counting by 3s, it's going to not be in the middle of the space. Okay, so just be aware of that. Also, when you're checking your homework answers, I put up the book answer key, so yours is going to look different anyways, but you can kind of look at some of the points they have on there. They're probably going to count by something different as well, but as long as your graph is matching up with that table of values, you are fine. The homework is actually in the back of the packet. 8.1 worksheet 1, because you need there's graphs on there. Okay. And this video will be up, so if you need to see the rest of it. All right. The next page has our word problems. They're really not very difficult. You're still using the equation y equals a times b to the x, but each variable is going to stand for something different. These exponential equations usually go with population growth, which grows exponentially. Also scientific things such as like how cells multiply or bacteria multiplies. Those are the types of things. Now A is going to stand for the initial population, which it could be of people or of bacteria or whatever the problem is talking about. It's your starting point. Now B is considered the growth factor. And there's a formula to find what the growth factor is. It is 1 plus R. R is the rate of increase. And the reason that this formula exists is if I were to say something increased 5%, you would multiply by 0.05 and then you'd add it back because it's increasing. So by doing this, you'll actually be giving me the adding back part, so you don't have to do that. So it's like 100% plus whatever additional percent. Also maybe jot down that this needs to be as a decimal. So example 3 says refer to the graph. In the year 2000, so let's look at the year 2000, the annual rate of increase in the U.S. population was about 1.024%. Suppose the rate of increase continues to be 1.24%. Write a function that models the U.S. population growth after the year 2000. So this is now our initial year. Our starting year is 2000. We're looking for after that. So I'm going to set up my equation, y equals a times b to the x power. The initial population was 281 million. So this is my a variable. Now to find the b value, I do have to do a little bit of work, remembering that b is equal to 1 plus the growth rate. Again, that's 100% of the population, and then r is how many we're adding to that population. Now we need to change this to a decimal by dividing by 100 or moving that decimal 2 spaces over. So it'd become 0.0124. So we get b is 1.0124. So plug that back into our formula. And then we use the exponent x. Now you do need to tell me what x represents since you're writing this model. X is going to be the number of years after 2000. That way the person who reads this model doesn't think that they're supposed to plug in like 2012. They just plug in 12 for x. So for part B, it says predict the U.S. population in 2015 to the nearest million. So that would mean that x is 15. So we just evaluate this equation. Plugging in 15 for x. And you'll need a calculator to do this, obviously. We don't know how to raise that decimal to the 15th power. And you're using the caret 15. Should get 338, and that would be, if you notice, this is the population in millions, so that's 338 million. It's all a confused face. I didn't put parentheses when I typed it in. You can put them or not, it's up to you. I just put them here so that you don't think you're supposed to multiply those numbers before you raise it to an exponent. All right, we'll skip over that next example because it's like the same thing. And we'll look at one of the last ones. And we can finish up the last few examples tomorrow if we need to. So the last one asks us to write an exponential function that includes these 2 points. So remember, both of the points are x, y's, because that's what points are. So you're going to follow the steps I have typed out. Start with the general form, y equals a times b to the x power. Pick one of your points and plug it in for x and y. So we'll have 4 equals a times b to the second power. We still have two unknowns. We have a and b. But what you're going to do at this point, we're basically going to solve by substitution. So at this point, we'll solve for a. So we'll undo multiplication of b squared with division of b squared. So I'll get a equals 4 divided by b squared. Now take and rewrite this equation again. Y equals a times b to the x. You're going to take this expression and replace it for a using like the substitution property. So I'll end up with y equals 4 divided by b squared times b to the x. Then you plug in your second point. So my second point, 16, will go in for y. 4 divided by b squared stays. B to the x will become b to the third. Then you use your exponent rules. If we're dividing exponents, because this is really b over 1, we subtract. So 3 minus 2 would just be b to the first. To solve for b, we would divide by 4 on both sides. So we'll get b is 4. Take that value, plug it back into the a equals formula to find out what a is. So I'll get 4 divided by 4 squared, which is 4 over 16, which is 1/4. That's my a variable. Taken final answer, we plug those back in to make our equation. We'll get y equals 1/4 times 4 to the x. You cannot simplify that. Don't think you can make that 1 to the x power. Homework is 8.1 worksheet 1. It is at the end of the packet. It's like the second to last page. I will finish doing these examples during my study hall, and then I'll post the video in case anyone needs to see all of them.